Okay. First, let's review what a vector space is. A vector space is made up of a set. Um, there are two sets which may or may not be the same. Um, the real numbers is one of the sets, though we could have complex numbers in its place. The set of the actual vectors, so we have to have those two, an addition of the vectors, and a multiplication of these numbers with the vectors, the scalars. This is the set of scalars. Yeah, set of scalars. This is the set of vectors. And then we have to have an addition and a scalar multiplication. By that, what we mean is we multiply vectors with scalars or scalars with vectors. And we have to have 10 different properties. Some people count them as 8, some people count them as 10. It depends. So we have to have certain properties. If we fulfill all of those properties, then we have what is called a vector space. So a vector space is defined by a set of items or things with certain properties. If you notice those properties, then we call that thing a vector space. I mean, this is kind of a silly analogy, but it is like if you see something that quacks like a duck and looks like a duck and behaves like a duck, then we call it a duck. Well, that's kind of like what we are doing here. We're defining what a vector space is supposed to look like, supposed to quack like, or supposed to behave. And it is actually very, very simple. Even though there are 10 properties to view, it is much simpler to look at a mathematical object and identifying it as something such as vector space as opposed to an animal. So for instance, yeah, because the animal you can do many things to it. You can disguise it so it doesn't look like an animal. I guess a vector space you can disguise it too, now that I think about it. In fact, that does happen often, as we will see in some examples. So as we get into linear transformations, we have to review what a vector space is. The addition has to be closed. So the addition, I'm just going to abbreviate that with a plus. So addition must be closed. What that means is that if you add two vectors, the result has to be a vector. It cannot spill out over something that is not a vector. So two vectors added together should be a vector. The addition should be associative, must be associative. So that means if we add two and then add a third one after adding the first two, if we group the vectors differently, add the last two first, and then the first one added to the sum of the last two, it doesn't matter which way we go we do the addition, the result is going to be the same. So that's what we mean by associative. The addition must be commutative, must be commutative. That means that if you add two vectors one way or you add them the other way, this sum is going to be the same. The next one is a little weird. The addition must have a neutral element, has to have a neutral element. So the operation has to be a neutral element. What I mean by a neutral element, better known as identity element or identity element, means that there is an element in the set of vectors so that any other element added to that element that we're talking about, the neutral element, gives you back the original one. In other words, we oftentimes call it zero. Or I'm going to put zero because it's not the zero of the real numbers necessarily. Oftentimes it isn't. It is the zero of the vector space. We have to distinguish between those two. most of the time, those two are not the same kind of set. In fact, very seldomly we think of them as the same. Okay, so we got 1, 2, 3, 4, and then every element has to have an opposite. So addition. Now, wait a minute. Must have. This is, even though this is a property of addition, it is really V comma plus. So V under plus, V is the one that has the element that is neutral. And V and plus, again, must have opposites. Yeah. Notice that here I'm using plural. Here I'm using singular, neutral. So one neutral versus many opposites. Every element in V has to have its opposite. What is the opposite? It is the one that added to the original element gives you the neutral element. I know this is a little bit weird to talk about because we are talking in the abstract. We are only talking in terms of what things do, not what they are. So we got 1, 2, 3, 4, 5 properties. I mentioned 10, so there are 5 more to go. We have to have a scalar multiplication that is closed. So a scalar, oftentimes we use the actual symbols. Let me put a bullet here, bullet 1, bullet 2, bullet, bullet, bullet. So I'm going to do another bullet here. So a scalar k, which is a real number, times a vector must be in V, must be a vector. So when we multiply a scalar times a vector, we have to end up with a vector. Again, this is closure. Yeah, scalar multiplication must be closed. Scalar multiplication must be closed in V. Yeah, because somebody could say, well, why cannot we ask the vectors, the multiplication to be closed in R? So multiplying an R number, I mean a scalar, which is a real number in this case, times a vector, why cannot we ask it to be back in the real numbers? We could, but then that is not a vector space. We have to go back to the vectors. So that's 6, 4 to go. The next one is kind of silly. However, it is necessary. The scalar number 1, because 1 belongs to the scalars, times any vector gives you back the same vector again. So that is almost, it may seem unnecessary, but it is necessary. Without this, we don't have a vector space. We have to have 2 kinds of distributive properties. So 2 scalars distributed over a vector V gives you AV plus BV. So it's understood. I'm being a little bit vague, not very formal, because I'm telling you, I'm speaking up that those 2 are scalars while V is a vector. And so we can distribute scalars over vectors. We can distribute 1 scalar over 2 vectors. So V, W, let's pretend those are 2 vectors. We can multiply with the scalar and have AV plus AW. And we have to have comparability between scalars among this, between the scalar multiplication among themselves and the scalar with vectors. So the multiplication has to be comparable. What we mean by that is, if we do a scalar product of A times a vector who happens to be a scalar product of another scalar times a vector V, so this is the only vector V, well, multiplying with a scalar gives you a vector, and multiplying with another scalar again gives you a vector. Well, the multiplication between A and BV is between a scalar and a vector. That should be compatible compatible rather with the multiplication among the scalars. So AB multiplied with V, so that's one scalar times a vector, should equal to the vector times the second scalar. In turn, that new vector multiplied with the first scalar should equal that. And that is all the properties of vector spaces. Now, most of the examples that we encounter have to do with r to the n. So for instance, as an example, we have r cubed. So that is the vector. The addition is the addition of vectors. The multiplication is the multiplication by scalars. And the scalars themselves are r. So what are the elements of this vector? Well, the elements of the vector are things that look like this, maybe 7, -2, I don't know, 5. So that is one element of this vector space. If we add with another vector, so again, I'm being very informal. I'm just going to talk about this lightly. Let's say we add with another one, -2, 0, 1, for instance. Then we obtain a vector. 7 plus -2 is 5. -2 plus 0 is -2. 5 plus 1 is 6. And then we can multiply any vector, say this vector, by a scalar, 7, -2, 5, multiplied by any scalar you want, say pi. That gives you a new vector, 7 pi, -2 pi, 5 pi, there. And the thing is, if we further multiply this with another scalar, e, for instance, so then we're going to have e, rather 7 e pi, -2 e pi, 5 e pi. Well, that is the same thing as multiplying by e pi at the outset of this multiplication. So whether you multiply after the first multiplication or after a second multiplication, it doesn't matter. We still end up with the same thing. We have to have a 0 vector. Okay, so a 0 vector is, in this case, is going to be 0, 0, 0, because if we add this vector to any, say those two vectors added together, is going to give you back this vector. That's why this is 0, because added to this vector gives you back this one. What else? Oh, and any vector has an opposite. So this vector, again, this vector that I'm pointing to has its opposite, and it would be -7, +2, -5, because if we add those two vectors together, we end up with a neutral vector. And then we have associative and associatives, and we have distributive rules. They're inherited from R. So we're, we can verify the other rules without too much work. Actually, I shouldn't say that. It is a lot of work to verify all the rules, all the properties. I take that back. It is work. It is kind of tedious to do that. It is necessary also to do that. Another example is, for instance, the set of 2 by 2 matrices, square matrices. So this 2 implies 2 by 2 real matrices. That's a vector space. Oh, before I move on, we can say more about this vector space. The dimension is 3 because we can find 3 vectors that span R cubed that are linearly independent. So the vectors that span R cubed would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Those 3 vectors can produce any of those while being linearly independent. If we find a set of vectors that can span all of the vector space while being linearly independent, then the number of those vectors gives us the dimension of the vector space, in this case 3. If you have 2 by 2 matrices, then that is a vector space as well, You know, we can have a matrix 2, 3, 7, 1, and then its opposite will be -2, -3, -7, -1. Oh, before talking about opposite, we have to talk about the zero matrix, which would be 0, 0, 0. And then adding those two together, we get this one. We can multiply by a scalar, which means multiplying every one of the elements by the scalar. So this is a vector space, all the set of all those matrices. What is the dimension of this vector space? This one. Well, we have to have addition of matrices, multiplication by a scalar, and the real numbers are the scalars themselves. Well, it is 4 because we can find 4 matrices, 0, 1, 0, 0, 0, 0, 1, 0, and of course 0, 0, 0, 1. Those 4 matrices generate any matrix, 2 by 2 real matrix, and they are linearly independent. Now, it doesn't hurt to review what we mean by linearly independent. So let's go back to example 1. Going back to example 1. Why do we say 1, 0, 0, 0, 1, 0, 0, 1 are linearly independent? Well, put 3 numbers, make a linear combination that equals, put together a linear combination that equals 0, which is 0, 0, 0. Okay. If this is the case, and if that equation forces A, B, and C to be 0, all of them, that means that the 3 vectors are linearly independent. That means that there is no redundancy within the vectors. Yeah, this is equal to A, 0, 0. If we multiply A times 1 is A times 0, 0, A times 0, 0, plus 0, B, 0, plus 0, 0, C. And that is, of course, equal to A, B, C equals 0, 0, 0. And 2 vectors, 2 column vectors are equal if their corresponding entries are equal. And that means that A has to be 0, and B has to be 0, and C has to be 0. So if the only way we can get the 0 vector is by having all of the coefficients 0, that means that the vectors themselves are linearly independent. The same thing applies to those 4 for linearly independent. The reason why I brought it up is because this vector space has dimension 4. Let me show you another vector space that is less obvious, at least initially. 3. Let P sub 2 be the set of all polynomials in one variable, say x, of degree less than or equal to 2. Now, before we continue, let's make sure we understand. So we have, all the polynomials such as 7x squared minus 3x plus 9. So that's a polynomial of degree 2. And there are many polynomials like so. Or if you have 5x minus 1, those are polynomials of degree 1, polynomials of degree 2, polynomials of degree 1. And we have many of them. And then we have polynomials of degree 0, which are just plain numbers, such as 7. 7, mind, is a polynomial. It's a polynomial of degree 0. So that is also a polynomial. We think of polynomials as functions, by the way. In this context, think of polynomials as functions. So A polynomial, a quadratic polynomial will be a parabola opening up or opening down. A linear polynomial will be a line that is oblique or horizontal, and it could have a positive slope or a negative slope. And a number, ooh, what is a number? Actually, a number is going to be a function that is going to be always horizontal. So I take this back. I think I mentioned that linear polynomials can be oblique or horizontal. I take that back. They can only be oblique with a positive slope or with a negative slope if they are linear. If they are constants, then we have horizontal functions. So we have all the functions, mind, they're not vectors like with, they're not, see, this is a vector. That's what I'm trying to say. This is a vector. This is a vector. So from the abstract point of view, in the sense that a vector is not what we used to think, oh, like 3, 1. That's one kind of a vector space, the one that looks like this with points on the XY plane or XYZ plane, yes. But then we have those are vectors in the sense that this set has an addition. We can add 2 of them. By the way, if you add a parabola with linear, you're going to end up with another parabola. A parabola with a constant is going to give you another parabola. It's a shift. 2 linears give you a linear. 2 constants give you a constant. A linear and a constant give you a linear. So there's some rules, but they don't necessarily belong to the vector space itself. They just happen to behave in a certain way. What else can we say? Oh, the opposite of this polynomial will be the one with the same coefficients and negatives, opposites, -7, for instance, plus 3 minus 9 as coefficients will be the opposite of this. What is the zero vector? The zero vector is the one that is horizontal right on the x-axis. So this, which is the function 0, is a vector. Okay, so you gotta be open-minded, very, very open-minded. So a vector could be, so we're still in the same example. So still in p squared, no, not p squared, p2. Yeah, you gotta be open-minded because a vector could be x squared. And by that we mean the function x squared, or a vector could be x. So let's label this as little p2, little p1, and then we can have little p1. Oh, that I meant to say 2, 1, oh, 0, p sub 0. There we go. Yeah. So let's just make sure we understand. So little p2 of 7 equals 49. Now, I'm not stating that this is a vector. The vector is all of that. So a vector is a whole entire function with its whole domain and its whole range and behaving as it behaves. It is a whole x squared. And you can plug in numbers into this one vector. You can plug 7, or you can plug -7. P sub 2 of -7 is still positive 49. P sub 1 of 7, this function is just 7. P sub 1 of -7 is positive 7. No, I take that back. It is -7 because the output is the same as the input. P sub 0 of 7 is going to be 1 no matter what. P sub 0 of -7 is also 1. All right. So this is a vector space, the set of all the polynomials of degree 2 or less than 2 is a vector space. Now, I claim those 3 are linearly independent. So, before I continue, let me introduce Q, the polynomial Q of X. I cross my Q's, by the way, just like I cross my Z's. I know it is kind of weird for some people to do that. But I do that because I want to distinguish the Q's from nines. That's my way, my personal way of distinguishing Q's from the number 9. Anyway, I'm introducing 0. So this is the function 0. This is not the number 0. This is the function 0. See, the number 0, we can point to it on the number line. It is a dot. There it is, 0. But Q of x, the function 0, is this line, is the function Q of x equals 0. So, what is Q of 1? 0. What is Q of 2? 0. What is Q of 3? 0. So, all of those points, 0, 0, or 1, 0, 2, 0, 3, 0, and all the points in between, and -1, 0, and all of those make up this long line. This line has an infinite number of points. All of those, that one set of all of those points make up one vector. So the whole line is one vector. So don't confuse that with the number 0, which is just one point, versus the whole entire line. I know this is weird because we're not used to thinking of vectors as anything other than, just the little arrows that we do in physics. But this is a vector. And yeah, it is too bad that we introduce vectors, that we put too much emphasis on vectors as arrows, as in physics, because vectors are much, much rich. Matrices are vectors, for instance, but we don't think of them necessarily as vectors. And by vectors, we mean vectors as in a vector space. So a vector space is any set with those 10 properties. That's what we call a vector space, and any element in a vector space is called a vector. So we are opening our mind to allow more things to be in the set of vectors, to be called vectors. Yeah. What else was I going to say about this? Oh, linearly independence. Yeah. So how do we prove that those 3 vectors are linearly independent? Well, multiply A with x squared plus B x plus C equals 0. C times 1. So x squared, x, and 1 equals 0. But this is not the number 0. This is the function 0, not the number 0. Not the number 0. See, many of us may be thinking, oh, all I have to do is apply the quadratic formula, and then I can find the values of x. No, 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 no. Do not confuse that. This is a function equivalent to a function, not a set of numbers that give you 0. We're not trying to plug a number into x. This is true. I guess the difference between solving a quadratic equation and thinking of this as a vector is this equation is true for all and every value of x. So if x is 5, this should be true. If x is 7, that should be true. If x is -18, that should be true, because we're talking about the function 0, not the number 0. This should blow our minds because it's completely different than what we did ever before. Okay. So let's just quickly prove this. This doesn't take long. So we can set x to be 0 because this is true for all and every value of x. If x equals 0 in particular, then, okay, we got a times 0 squared plus b times 0 plus c times 1, which is just c, equals 0. But of course, that is 0. So the conclusion of that is that c is equal to 0. This symbol means then. It's a special symbol we use in math, and it means then, or implies. So this implies that, or if this, then that. Okay, so now we know that C is equal to 0. And we can rewrite our original equation as, now that we have that knowledge that C is equal to 0, we can rewrite, rewrite original equation as ax squared plus bx equal to 0. And that is true for all x, all and every one of the x's, because we're talking about the function 0, not the number 0. Very, very important distinction. So in particular, if x equals 1, then we have, well, 1 squared is 1 times a, 1 times b is b, plus b equal to 0. If x equals -1, then -1 quantity squared is 1 times a is still a, -1 times b is minus b equal to 0. And those two equations are true because that equation is true for every single value of x, which means we can add those two equations, add those two equations. So that means that 2a, no b, because when we add b with negative b, we get 0, equals 0. That implies that a is equal to 0 because we can divide by 2. And if a is 0, then this equation becomes b is equal to 0. Let me label this equation as equation, I don't know, star. So star yields a is 0, so b is equal to 0. So c, what is it? C is 0, and so is a, and so is b, and consequently, the three functions x squared, x, and 1 have to be linearly independent. X squared, x, 1 are linearly independent. And then any quadratic polynomial can be written in this form precisely, without the 0, of course, but every polynomial of degree 2 is precisely ax squared plus bx plus c. So that means that those three are linearly independent, and they also span all of the polynomials of degree 2, and consequently the dimension of P2 is equal to 3 because we need 3 elements to span, while those 3 elements are linearly independent. Let me give you one more example, which is a weird example, but it is reasonably well known. Example 4, the positive real numbers addition, but we have to have a special addition. And the special multiplication by scalar. Let's make it a little square. Yeah, so this is the multiplication by scalar, and this is the addition. Let's make it a square also. So let me start all over again. So example 4, all the positive numbers, so not 0, a new addition and a new multiplication by scalar, and the scalars are going to be r. Now, there is very little negotiation with the scalars. The scalars have to be either r or the complex numbers, occasionally they can be some other kind of set, but the set has to be very special in the sense that it has to have opposites, negatives and opposites and things like that. This set can be very wild. It can be many different things. It can be, yeah, this set, like the polynomials, we can have continuous functions, we can have this. This has to do with a little bit with logarithms and exponential functions. So if we define an addition, if you have two positive numbers, no, let's call them V and W, and we want to add them together, we can just multiply them together. So that is the addition, that's V plus W. So two positive numbers added together can be the product of those two numbers. If you have a constant, say A, scalar multiplied with V, we can rewrite this as V to the A. Yep, and that defines a vector space. Yeah. I'm not positive, but I might ask you questions about this in assessments, about this particular set. But what I'm trying to tell you is that polynomials, matrices, regular vectors as the way we know them, all of those are vector spaces. The reason why I'm pausing is because now I'm puzzled. I didn't think of the dimension of this before. So when are two elements? I have to think about that. Oh, the dimension is 1. Because every element can be written as a product of R. Yeah, the dimension is 1. Yeah, because we're multiplying with R. Every positive number, you can get to any other positive, from one positive number to another positive number by multiplying by a scalar. Anyway, but let's talk about linear transformations. So typically we label with T a linear transformation, and we use this notation to say that a linear transformation goes from one vector space V into another vector space W. So those two are, at this point, we're going to assume they are real vector spaces. That means that the scalars are going to be real numbers, real vector space, and that is another real vector space. Now, when I say another, it could be the same. It could be a copy. This vector space could be a copy of this one. So this is the notation indicating that this is a function. By the way, this is a function or a map. And it will be a linear transformation if we have two properties. If T preserves addition and T preserves multiplication by scalars. Sometimes they write this in one equation. I like to separate them into two, but many books write that into one equation. I just like to separate it into two. Okay. There are many things that are not linear. Watch out. Yeah. Many functions are not linear. Okay, let me give you examples of nonlinear functions first. So example 5, something as innocent. Okay, so let's say we define f from R to R. That means R to the 1 to R to the 1. Okay, by, f of x equals 3x plus 4. This is not linear. Oh, this is confusing. I'm glad I brought this up as an example. I'm getting excited because it is a good example in the sense that this example is confusing. I'm going to tell you why. Confusing example. Okay. It is linear as in regular algebra, college algebra. It is a linear polynomial. Okay, so f of x equals 3x plus 4 is a linear polynomial. Any linear polynomial has the form mx plus b. There is m and there is b. So where is the problem? It is linear. There's no problem. However, f of x equals 3x plus 4 is not a linear transformation. It is not a linear transformation. It is a linear polynomial, not a linear transformation. The same function. And that, I have to admit, is confusing. So you know why this is linear as a polynomial, because it has degree 1. There's many ways to describe it. Also because it has that form, mx plus b. Also because when you graph it, you do get a line, some kind of line. So yes, it is linear, a linear function, a linear polynomial, but not a linear transformation. So the key is combining linear with transformation. Why not? I'll tell you why not. What is f of 5? F of just a random number 5. Well, that is 15 plus 4, 19. Okay, what is f of 6? Just to follow up with the next number. Well, 3 times 6, 18 plus 4, 22. Okay, let's add the 5 and the 6 together. We get 11, correct? So what is f of 11? Now, if you think it is 41, because 5 plus 6 is 11, and somebody may think, well, that means that when you add those together, you get this answer, 41. Isn't it? Let's put a line here and 41, an addition. No, it's not. Think about that. 3 times 11 is 33 plus 4 is 37. That's one of the reasons, but one is enough. This is sufficient reason for this transformation, this function, not to be linear. If you add two numbers and you don't get the corresponding addition of the addition of the corresponding outputs, that's what I meant to say. If you add two inputs and the output of that addition of inputs does not give you exactly the addition of the corresponding outputs, we don't have linearity. That's sufficient. That breaks the deal. And all it takes is one thing to break the deal. If I ask you, and I'm likely to ask you, why is this not a linear transformation? Please, two things are going to be very important. Give a concrete example with numbers such as 5, 6, 19, 22, 11, 37, and 41. Give concrete examples with concrete numbers. Don't be using A's and B's and C's or X and Y's and Z's. Don't use variables. To break the rule, all it takes is one concrete example and then you're done. Don't give more than one example because you're going to be judged on the overall thing. So if you give me two examples and one is not a good example for one reason or another, then you're going to be judged on both. So one is enough. I'm going to give you a second one, but please bear in mind that this is enough. This breaks the deal. And stick with one. Don't overkill. In logic, in mathematics, when we are disproving something, we don't want to overkill because we're going to be judged on everything. So we risk saying something that is not accurate or logical. All right. Plus, it is not necessary anyway. So if it's not necessary, then we don't do it. In mathematics, I'm not saying that is always the best philosophy or policy. Okay, so that is one reason. This is enough to show that this f is not linear. Now, somebody else could say, okay, I have another way. F of 5 is 19. We don't have to redo it. There it is. If we double the 5, we get 10. F of 10, well, 10 times 3 is 34. 34, but it's not twice. We double the input, but yet when we double the output, we don't get the correct output. If we multiply by 2, we get 38 and instead of 34. Again, that breaks the deal. If you can find one example in which addition is not preserved, so this is what I mean by addition being preserved. Here, when we add here, after the f, we don't get the addition of the outputs. Or multiplication by scalar preserved. If we multiply by 2, we don't multiply the outputs by 2. Then we don't have a linear transformation. 6. So what is a linear transformation from R to R? If that one wasn't, which one is it? Let me give you an example. F going from R to R, defined as f of x equals 3x without the 4. That is a linear transformation. Then we're good. Why? Okay, so if you have f of a plus b, well, that is 3 times the input, because that's what the formula calls for, a plus b. But then the real numbers allow us to distribute. So this is 3a plus 3b. But that is really f of a plus f of b. So whether you add in the input or in the output, we're good. That's what we mean when we say that the addition is preserved under the function. If we multiply by a constant, say k a, well, that is 3 times by the formula k a, but these are real numbers, so we can reassociate. I'm going to go the long way. We can say 3k a. We can commute k 3a. We can reassociate. I know this is confusing there. And that is exactly k times f of a. So if the k can factor out, that's what we are trying to do. If the k, a constant, can factor out, that's good. If the addition can sort of factor out, then we're good. This is a linear transformation. Multiplying 3 with x is a linear transformation. It's a very good linear transformation. As soon as we shift, as soon as we add 1 or 2 or 3 or 4, or any number, doesn't have to be, or subtract minus 1, it doesn't matter. The linear transformation, the linearity, right, there you go. The linearity fails. Yeah. Yep. If you have a vector space r to the m, so this is example 7, into r to the n, we can define a linear transformation by multiplying with a matrix A. So let's label this as T with a index A. Okay, so we're taking R column vectors that are dimension m. So the matrix A has to be n by m. And different books use m and n differently, so watch out. But if you have m in the source vector space and n on the target vector of the transformation, then the matrix we multiply by is gotta be m by n. And we can define t of the vector x, t sub a of the vector x, as ax. That is a linear transformation. And the reason is because multiplication by matrices is distributive, and multiplication by scalars, by constants, factor out, just by regular scalars, factor out. So that is a linear transformation. Furthermore, every linear transformation from Rm into Rn may be defined this way. That is a theorem. That is a fact. It's been proven without any doubt. So all the linear transformations from Rm into Rn may be written as a product with a matrix. Yeah. Moving along this way, okay, find the matrix, let's label it A, corresponding to T, which will go from R squared into R squared, such that T of 1, 1 equals 1, 2, and T of, I don't know how much I want to play with this. Let's not play too much. So 2, 3 equals, we don't want to put the same vector. We want to put something else. So how about 2, 5? That's not an easy problem, but let me explain to you this one, because we want to be able to come up with the matrices that produce this. Yeah. I'm trying to think how I'm going to explain this. So this is the way we usually go about it. To find a matrix A in general, find a basis of the source vector space and the target vector space. So, R squared has bases 1, 0, and 0, 1. And so does R squared. 1, 0, and 0, 1. So, okay. If you map 1, 0 using this transformation, the output you get is going to be the first column of A. In other words, A is going to be equal to T of 1, 0. That's the first column. And the second column is going to be T of 0, 1. Yeah. So if you map base elements with T, the columns that you obtain are going to be exactly the matrix A. that produces that transformation. Let's be a little more practical and actually figure out how we're going to do this. Now, so the next question we want to ask using this idea is, how do I find T of 1, 0? Okay, so the next question we want to ask based on this is, what is T of 1, 0? Question mark. We know what T of 1, 1 and T of 2, 3 are, but I don't know what T of 1, 0 is. Okay. Again, I'm going to repeat what I just said. We know the problem tells us what T of 1, 1 and T of 2, 3 are, those, but we do not know what T of 1, 0 is. I want to figure out what T of 1, 0 is. So what we do is write 1, 0 in terms of 1, 1, 2, 3. Because we know how to handle those guys. I don't know what 1, 0 is, but if I can rewrite 1, 0 in terms of those two guys, then I know how to handle the T. Okay, so the first task is to figure out, I'm going to use A times 1, 1, the vectors they gave us, 1, 1, and B times 2, 3, that give us 1, 0. Okay, so that means that A plus 2B equals 1. A plus 3B equals 0. Oh, we can subtract this and add this. Yeah, so 3B minus 2B is B. A minus A is no A. And 0 minus 1 is negative 1. Okay, so if B is negative 1, then we can figure out A. A number minus 2 equals 1. This A has to be 3. Okay. So what we know is that 1, 0 may be written as 3 times 1, 1 minus 2, 3. Yep. We can check. 3 minus 2, 1. 3 minus 3, 0. So T of 1, 0 equals 3 times T of 1, 1 Yeah, can't erase. Let me just scratch. Doesn't look as nice, but 3 T of 1, 1 minus T of 2, 3. That's what linearity does. If we know T is linear, and they're telling us in the problem that T is linear, if you know this vector is equal to that linear combination, when we apply T to that vector, that is the same thing as applying T to this one and this one individually, this vector and this vector individually, subtracting, the same thing as adding. And within this vector, we can factor out the 3. Okay. And we know how much T of 1, 1 is because they told us T of 1, 1 is 1, 2. So this is 3 times 1, 2 minus T of 2, 3. T of 2, 3 is 2, 5. So that means we have 3 minus 2, 1, 6 minus 5, 1. Oh, that is interesting. 6 minus 5, 1. So that means that A, remember, we're looking for a matrix A. The first column is 1, 1. Now we're searching for the second column. But we proceed in the same way. So the question is, what is T of 0, 1, which is a base element, on the second base element? Well, we don't know. All we know is that T of 1, 1 is 1, 2, T of 2, 3 is 2, 5. Okay. Can we write 0, 1 as a linear combination of 1, 1 and 2, 3? 1, 1, x plus y 2, 3 equals 0, 1. Can we do this? Well, let's find out. Let's solve the equation. This means that x plus 2y is 0. X plus 3y is 1. We can subtract the first equation from the second equation. X minus x, no x. 3y minus 2y, y. 1 minus 0, 1. So if y is 1, x has to be negative 2 because they have to add up to 0. X equals negative 2. Okay, so 0, 1 is equal to negative 2, 1, 1 plus 1, which we don't necessarily write it down, 2, 3. And remember, our goal is to find T of 0, 1. T of 0, 1 is equal to, well, let me write it this way. T of negative 2, 1, 1 plus 2, 3, which is the same thing as negative 2 T of 1, 1 plus T of 2, 3. And that is equal to negative 2 times T of 1, 1, they told us, is 1, 2, plus T of 2, 3 is 2, 5, so that is 2 minus 2, 0, 5 minus 4, 1. Oh, what a coincidence. T of 0, 1 is 0, 1. I did not plan that. So A, which is what we're after, A is equal to, oh, in the previous page, one of the previous pages, I had mentioned that A has the first column of 1, 1. The second column, we just found it to be 0, 1. Okay, multiplying by this matrix is the same thing as transforming with this T. But let's check. So this is the matrix that we are looking for. But let's check. If it is so, then when we multiply 1, 0, 1, 1 with 1, 1, we better get 1, 2. I'm going to pretend I don't know what I'm supposed to get. 1, 0, 1 plus 1. Do I get the same thing I'm supposed to get? Yep. Checks. 1, 1, 0, 1 multiplied with 2, 3. Okay, I'm going to pretend I don't know what I'm supposed to get. 2 and 0, 2, 2 and 3, 5. Yep, it gives us 2, 5. Checks. That means that this is the matrix. Now, what do we gain with this? Oh, we gain tons of work, tons of things, tons of everything. If you give me any vector whatsoever, you know, give me a random number or a random vector, 7, 8, and you want to find T of 7, 8. You know, the long way of doing T of 7, 8 is to figure out how to break up 7, 8 into those two, and then, as you know, as we did earlier, just to find the columns. In this example, in example 8, how did we find, how can we find how to map 7, 8? Okay, let me show you. So there's the long way and then there's the short way. But once we have the matrix, there's the short way. So first, the long way. Okay, find two vectors x times 1, 1, or two scalars, and y times 2, 3, that gives us 7, 8. Okay, that takes a little bit of work. So x plus 2y, I'm going to try to squeeze it in this space. X plus 2y equals 7. X plus 3y equals 8. Subtract second equation minus first equation. So y equals 1. X equals 5. Looking at this, 2 and 5 is 7. Yep. So that means 7, 8 can be written. So 7, 8 can be written as 5 times 1, 1 plus a 2, 3. Yeah. Okay. T of 7, 8 is consequently 5 times t of 1, 1. T of 1, 1 is 1, 2, plus t of 2, 3. T of 2, 3 is 2, 5. And then we have to put this together. 5 plus 2, 7, 10, plus 5, 15. Wow. So this is the long way to figure out the output of t of 7, 8, or the output of t the output of 7, 8 under t. Or the short way, once we have this matrix, then we can mass produce outputs. Just multiply 1, 0, 1, 1 by 7, 8, and that's it. You get 7, 15. Voila. It gets done in one shot. Instead of figuring out how to decompose into the elements they gave us, and then transforming each one of the elements by recalling the outputs and then putting it back together. Once you have the matrix, you got the whole transformation by simple multiplying, by simple multiplication of matrices. So this is the matrix corresponding to this transformation. And you can, if you have a linear transformation, you can always, 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 always find a matrix. Let's do another example very quickly with P2. So example 9, let me double check that it is actually example 9. I think it is example 9. So remember P2 is the set of all the quadratic functions. Yeah, where A, B, and C are real numbers. Okay. So that means that this A could be 0 or B could be 0 because they're real numbers. So they don't have to be strictly quadratic. They could be linear functions or just a constant or just 0. Okay, let's define the transformation D. We can label it anything we want. So we can call it D, which is going to be the derivative equals derivative of this function, of this polynomial. Every polynomial has a derivative. Okay, so the question is, what is the matrix corresponding to that, to this transformation? Find matrix. First, let's assume that the derivative goes from P2 into P2, because the matrix varies depending on the space and the target space, which is not necessarily obvious. Okay. We're going to choose x squared, x and 1 to be a basis. We can say c times 1, because this is to be consistent, ax squared, bx, c times something, which is going to be 1. So the base elements are going to be x squared, x, and 1. Okay, so we usually use this fancy b to denote the basis of the vector space, x squared, x, 1. All right. Now, remember how we did the matrix? The matrix corresponding to in the previous example. In the previous example, we found t of 1, 0, and that was the first column of A. And then we did t of 0, 1, which is another base element, and that was the second column, and that's how we found A. Well, we're going to do the same thing. This is a base element. So what is the derivative of x squared? 2x, which is 2 of those. Now, this is a little weird, but this x squared can be written as a column vector. Yeah, this is the same thing as d of 1, 0, 0. And by that, what I mean is 1x squared, no x, no constant. The derivative of 1x squared, no x, and no constant is 2x, which is no x squared, 2x's, no constant. This is the first column of our matrix. Now we're assuming the base is in this order. So once we come up with an order for the base, we gotta stick with that base order. X squared first, x, 1. If we reverse that, then the columns have to be reversed. So keep an eye on that. What is the derivative of x? Well, that is 1. Everybody knows that. But what does that mean in terms of this base? It means no x squared, 1x, no constant added to the x. And that gives us 1, which is no x squared, no x, 1 as the constant. 2 down, 1 to go. I cannot squeeze it in here, so I'm going to continue up here. So we got to do d of 1. What is the derivative of the number 1 or the function 1? 0. Everybody knows that. In terms of this polynomial, we have 0, 0, 1. That means no x squared, no x, just the number 1. Whoops, 0, 0, 1. Equals, well, the derivative of that is 0, which is 0, 0, 0. No x squared, no x, no constant. So the matrix, I'm going to call it B. The matrix B will be 0, 2, 0, 0, 0, 1, 0, 0, 0. So the derivative of any quadratic polynomial can be performed by simply multiplying with this matrix the corresponding coefficients of the polynomial. So this is the answer, but let's see what that means. Okay, so we're still in example 9. Okay, let's say you got a polynomial P1 equals 7x squared plus 11x minus 13. There we go. And I want to find the derivative of this using The matrix. Well, the matrix, let me copy it down, is 0, 2, 0, 0, 2, 0, 0, 0, 1, 0, 0, 0. It's very, it has a lot of zeros in it. If I want to find the derivative of this polynomial, remember this polynomial can be written as 7x squared, 11x's, negative 13. And now let's simply multiply. So we rewrite this polynomial as a vector. That's why we call it both a vector. This is a vector, this is a vector. Okay, so that is 0, 0, 0. Now let's multiply with the second row. 14, 0, 0, 0, 11, 0. So we can rewrite this as no x squared, 14x, and 11, which is correct. The derivative of this guy is 7, well, 14x plus 11. 14x plus 11. So this is d of P1. I know it is confusing to do all of this, especially since we know how to do derivatives. This seems like too much work to do a derivative. Yes, but we are learning how to do linear transformations and how to obtain the matrix of a linear transformation. And the derivative happens to be a linear transformation of polynomials. There are many linear transformations. Linear transformations are abundant. They happen in many places, especially in calculus. All right, with this introduction, well, we'll review initially vector spaces, and then we apply linear transformations to those vector spaces. Yeah. Yep. All right, with this, we will stop this video.